I'm Yunfei Luo. I'm a third-year PhD student in Halijulu Data Science Institute at UCSD, supervised by Professor Tauhid Rahman. And today I'm going to introduce our work on the first foundation model for the multivariate wearable physiological signals. And to begin with, there's a quick definition of foundation model, where it is a kind of a model that is flexible with the input format, and also it can be leveraged to a wide range of applications. And usually it is trained on a large corpus of usually unlabeled data sets. And we've saw success in the field of natural language processing, like large language model, and computer vision, where there's a lot of robust models. But there's still something missing in the physiological signal field. So the main challenge is because different studies and different data sets usually has different sensor configurations. So some studies focus on like brain waves, some focus on heart activities, some focus on physical activities, some having like a subset of sensors, like some having jointly like IMU sensors plus ECG sensors, but some has like GS, like Galvin's skin response and plus ECG. So basically there's different sensor configuration, and it's hard to kind of build a unified model for this. And also different studies focus on different features. Some focus more on the frequency domain, some focus more on the time domain. So that's why most of the recent works can like they're building model either for like one scenarios like sleep monitoring or just for ECG diagnostics. So our goal is to basically build a model that can be taking any of those formats and giving a like high quality representation output, and can be directly leveraged to a like more wilder range of applications. So I'm not going to dive too deep into the engineering detail, but on a higher level, we design a encoding block, which it will first encoding the input signals along the time axis, and then there will be a special token to serve as kind of a liaison for information exchange across different input channels. And then the exchange information will be sending back to the regular time domain encoder. And in this way, this kind of blocks can be taken input with any sequence length, any number of channels, and any order of sensors. And the whole model is made up by like stacking like multiple like 12 or 24 times of this kind of encoding blocks. And for the pre-training, we're mainly just following the regular masking and reconstruction setting, where the input model is like being segmented equally into patches, and some patches are being dropped out, and the model is asking for reconstruct those missing parts. And for the evaluation, we mainly evaluate on several scenarios, such as human activity recognition, fatigue detection, also cognitive affective states classification, also the brain EEG activity classification, as well as some heart-related disease risk estimation. So basically covering 11 widely used public datasets in literature, and covering like 18 commonly seen digital healthcare tasks. And as a quick overview to the results, so before we do the pre-training, we first collect data for the model, and we're basically crawling the internet and find as much public data sets as possible. And the main criteria we have is to make sure the data is like relatively equally distributed across different sensing modalities. So for example, we don't want the brain wave to dominate the representation of the model. So basically we have, for example, 1/3 of brain and neural related activity signals, and 1/3 of the heart related signals, and the rest for physical activity and the skin conductance. And after the pre-training, we conduct a quick analysis of the, as I said, there's a special token for the information exchange across the channels. And we just conduct a quick like TSNE plots on the representation, and we saw that the model itself can already differentiate different sensors. So basically, without any supervision, and we don't need to tell the model what's the input, the model can detect by itself what's the input, and then it will extract features accordingly for the downstream attacks. And across the 18 evaluation tasks, as I mentioned, we just basically show that our model significantly outperform all the most recent state-of-the-art models, including foundation models from time series domain, as well as those foundation models specifically designed for EEG and ECG and PPG. And also we've shown that the scaling law generally applies to our model, where it's generally with more pre-training data and more downstream data becomes available, and then the model performance will get improved continuously. And finally, we want to open box model, so we don't propose yet another black box model. So we just apply a nonlinear dynamical analysis on all the intermediate layers, and we find that the model can kind of extract more complex topological patterns across when the layer get deeper, and this also provide a theoretical a support for identifying how much of the parameter can be dropped out after the model is getting pre-trained. And yeah, and the preprints of the paper is available with an open source code base, and we hope the journal published version could be available soon. And we're also open to collaborations. And thank you for your attention.